So you know that free body diagram is very essential for us to understand how the internal forces, how the external forces will translate into internal forces. So yes, in the previous class I had given you a few examples of internal forces versus external forces, right? And with those examples, the sign convention for the forces for internal versus external should come. Okay, so in the previous class we were talking about, if I have a body A block, let's say, and a force is acting on this one. This is not an internal force yet, because whenever I say an internal force, I automatically also mean that that force is balanced, right? So when I'm just showing this force, it is not a balanced force, right? So this is just an external force which is acting on this body. Fine. So what would be the sign convention for this force? Would I say tension is positive, compression is negative? Will that be a sign convention? Acceptable sign convention? For this kind of a force?
Yes, sir.
Sure. Anybody else? Or I should say, rightward positive, leftward positive, negative. That might be a correct sign convention. So between these two choices, once we have tension compression, the other one is right left. Which one is the correct type of sign convention? I mean, of course, you can take opposite. You can take compression positive and tension negative. That is your choice. But this is one category of sign convention. This is another category of sign convention. Which one is applicable here for this force?
Rightward positive.
Rightward positive, right? Who is this?
Astula.
Okay. Astula, right? Yeah. Okay. Anybody else? No? Anybody else has anything to add? No? Come on, I mean, at least say that you agree with this or that. So there is one option here, second option here. Everybody has to tell. Sabullah has already told.
Second option, sir.
Second option.
The right word.
Okay. Vishal?
Yes, sir. The second
Yeah.
option, sir.
Second option. Yeah. So for this kind of a loading, or like when I present a situation like this, for this situation, you're talking about an external force. And the sign convention for an external force would be right positive and left negative, or left positive, right negative, whichever one you prefer, but not this one. This is not true. This is not applicable in this case. If I had given you this force, then you would have to say tension versus compression. Tension positive, compression negative, where it's automatically assumed whatever force P you are applying here, same force P you are applying on the other side. Then you can say tension positive, compression negative. Fine. So this is the sign convention to be used here. Similarly, I have a beam and I cut a segment of this beam. Looking at that segment, if I have a moment acting here, what would be the sign convention I would use? If I'm giving only this value.
Clockwise, anti-clockwise.
Exactly. So I can say anti-clockwise positive. And clockwise negative. Okay. And you have to be very mindful of this versus this. So whenever you are talking about a moment, you have to be careful whether you are talking about a moment standing alone, which is unbalanced, or you're talking about a bending moment. Okay. For this kind of a moment, what would be the sign convention?
Sagging hogging.
Sagging.
Sagging.
Right. So if it's a beam, you can very easily define sagging. If it's a column, you cannot define as sagging versus hogging. But anyway, you get the idea. So you pick one side. So if you pick the top side, so if the top side is in compression, you say it is sagging. If it is in tension, top side, then you say hogging. Okay. So now if you look closely, this bending moment in this case is made of two moments. Bending moment is made of two moments. One moment is anti-clockwise. The other moment is clockwise, right? That's why they are two balancing each other. These two are balancing each other because one is anti-clockwise, one is clockwise. This is clockwise, right? And that's why the sign convention used in this case is sagging versus hogging. And I have seen students and engineers, they are often confused which sign convention to use because when you're dealing with bending moment, you have to consider this sign convention. When you are dealing with a single moment, then you have to use this sign convention. Similarly for shear. So again, portion of the beam, force is applied this way. Okay. Only this force is given to you. We will use the sign convention of upward, downward. Okay. You can call it positive, you can call it negative. Your call. But if I am given this situation, okay, then basically what it means is that one upward force, one downward force, both are acting simultaneously. Then the sign convention would be whether this couple of balanced forces, they make the object rotate in clockwise direction or anti-clockwise direction. So your sign convention could be that this one I will call positive if it is making it go in the counterclockwise direction. The one that we use in this course is this one will be negative, and if it is this kind of a force, then it is positive shear force. Okay. So this is shear force. Sign convention. Okay. This is something you have to be very, very careful about. You should not be confused because in the same shear force, let's say the shear forces are acting as shown in this figure. Within this figure, you have one downward force acting, one upward force acting. So if you confuse this shear force with this force, then you would say, depending on where you are looking, you will say, oh, it is negative here, oh, it is positive here. So what is it? But then you are basically confusing it with an external force. It's an internal force, it's a balanced force, and the sign convention has to be taken as this one. Okay, I hope I have made myself clear. And this is why this sign convention is why, or the way you give them the signs is why you have to be very, very careful about whether you're talking about an external force on that body. So what is an internal force versus an external force? It's basically they are one and the same thing, but it depends on what you are looking at. Which part of the object are you looking at? Okay. So if I take a small strip here, then on that strip, maybe this force could be an external force. Okay. But then from this side also there is an external force. So if you're talking about this force all by itself, then you will say sign convention will be upward positive, downward negative. But if you're looking at this combination, then you will say this positive, this negative. Okay. Similarly, there is also a issue of torque, right? So torque is, you are all familiar with torque. Torque is applicable to, let's say you have, I'm not drawing a circle here, but you may as well have a circular cross section. And this is the longitudinal axis, and you have moment acting in this direction. Okay. So if the moment is only acting in this direction, then this is not torque. This is just one type of a moment about one axis. Okay, you can call it x-axis. So moment about x-axis. Okay, but if I have moment like this, and then also if I have at the same time a moment acting this way, which is opposite of this moment, in that case you will have a torque. Okay, and then you can give it a sign convention. In one case you are twisting it this way. So in this way, if you can imagine, this twisting is going to be like that. Okay, so this you can call positive. The other one would be negative. I'm not drawing it again, but you get the idea. So twisting in the other way, in the other direction, that kind of a twisting will be negative automatically. Okay. What kind of static analysis can be there? What kind of structural analysis can be there? Basically, can somebody try to answer what type of structural analysis or stress analysis can be there? The word structural analysis and stress analysis are just like, depends on how much detail you are getting into. Structural analysis from a structural engineering point of view, it stops when we calculate the internal forces, that is bending moments, axial forces. Stress analysis goes one step further and calculates the stresses also. So in finite elements, often we use the term stress analysis rather than structural analysis. Okay, but it also depends on which elements we are using. If you are using solid elements, you cannot get member forces. So what you get are stresses. But if you are using beam elements, then even in finite element also, you will get internal forces, which are bending moments, axial forces. So structural analysis and stress analysis, basically they mean the same thing, depends on the level of detail of your model. Okay. Now, what is the difference between static analysis and structural analysis? So this entire course that we are dealing with right now, it only deals with static analysis. So what is static analysis in comparison to the generic term of structural analysis?
Like the loads are time independent, sir.
Loads are time independent.
Then we call it as static.
Is the material also time independent? See, the material properties could be time dependent too. So if the material properties are time independent, then for the same constant load, you may have some kind of dynamic effect. So static is basically the opposite of static is? What is the
Dynamic.
Dynamic, right? And what does dynamics mean? Dynamics means velocity, accelerations, those things, right? So when we say static, when we mean that there is no acceleration or no velocity in the system. Displacements are there. So how can there be displacements while there is no velocity? We all know that velocity is a derivative of displacement, right? And acceleration is a derivative, time derivative of velocity. So how can we get any non-zero displacement without giving any velocities? So initially we know that system had zero displacements. We didn't apply the loads. Displacements are zero. Fine. Agreed, everybody?
Yes, sir.
Yeah. So displacements are zero to start with, and then you applied the loads, you got some non-zero displacements. How could that be possible without applying any velocities? What is the catch? I'm saying I'm doing a static analysis. No?
The velocity may be too low to consider.
Exactly. So basically, what we say is that it is not really stat. Most of the real, so for example, in the analysis, we assume that velocity is not there. And in realistic situation, what happens is that we are assuming that we are applying loads so slowly. We were at zero load value and then the loads were applied, but the load application was so slow that, or so gradual, that the velocities were very, very small, almost negligible velocity. So we never attained much of a velocity or much of an acceleration. Okay. So as a result, there is no dynamic component of the response. The response is almost static. It is also known as quasi-static. Okay, because it's not truly static. So any experiments, when we do any of these experiments, we apply the load, but we have to make sure that the loading rate is slow enough so that there is no dynamic response. Okay. So no dynamic response is again an inaccurate term. There is very little dynamic response, which does not affect the overall system response. Okay. Now within dynamic analysis, so static analysis can be done. Basically, static analysis basically means that you satisfy force equilibrium. Your A terms, acceleration terms are 0. F is equal to ma, right? So A term remains almost 0. So your F is equal to net force, total force is always 0. Okay, and that's what you try to satisfy in your static analysis, equilibrium equations. Okay, when you violate the condition of static analysis, then that's when you start to get some non-zero A values, acceleration values. Okay, and then you have to satisfy the dynamics equations. So that's when the structural dynamics comes into picture. I don't think you are taking structural dynamics this semester, right? Next semester it will be offered. Are you taking that already? No, you are taking elasticity. Yeah. Next semester you have dynamics. Okay, moving quickly forward, I wanted to also spend some time on determinacy versus indeterminate systems. So one by one I'll go because this is a very basic thing which you must have prepared or learned about for last 4 years quite a bit, and during the GATE preparation also you must have really been taught about this. Mohan Paletti, can you tell us? Can you tell us what is the difference between static system and the determinate system and indeterminate system?
Yeah, in the indeterminate system, equilibrium equations are sufficient to determine the internal forces.
Okay. And
in the
indeterminate
system, we need some extra equations in the form of compatibility equations.
Okay. So, like, sounds interesting, sounds quite intriguing, but does this definition of determinate versus indeterminate mean anything to you physically? See, I mean, I understand mathematically these equations are enough or they are not enough, but what does that mean physically? I mean, if I give you a system, can this definition help you figure out whether this is a determinate system or indeterminate system?
Yeah,
okay.
yes,
Yeah, it can, right? Yeah. So basically, there are some methods to calculate that. Okay. Anybody? Fine. Mohan. Anybody else? Maybe I'll pick the name. Ranjit, you have been rather quiet. So, Ranjit, that's your first name, right? Ranjit Kumar.
Yes, sir.
Yeah. So, can you tell us some other definition or some other way to know, other than that? Okay, this system can be solved using only the equilibrium equations. Do you have any other way of telling that this is a determinate system?
No, sir, like.
Sorry?
Sir, whatever the moment said, that was the only thing I know.
Yeah, that's what I'm saying. So that is okay. That is one definition. Any other definition you don't know, right? Okay. Tekeshwar Rao?
Yes, sir.
Yeah. Do you know anything else? Any other definition or any other way of telling whether this is a determinate system or indeterminate system?
Is anything about static indeterminacy, kinetic indeterminacy?
No, I'm not talking about kinetic indeterminacy yet. I'm talking about only static indeterminacy or static determinacy. So between an statically determinate versus indeterminate system, okay, how would you identify? One is that, okay, equilibrium equations are enough to solve the system. Any other way of knowing? Prithvi?
Yes, sir. Adding to what Mohan said, to static determinate structures, if there is any small abnormalities in the structure, that will not affect the stresses, the internal stresses in a static determinate structure, sir. And that will affect considerably into the static indeterminate structures.
Can you elaborate on what you mean by effect?
Like if there is any thermal, if there is any the thermal loading, that has a very less effect on the static determinate structures when compared to the static indeterminate structures, sir. And at the same time,
Again, I understand the first part. I'm saying effect. When you say very less effect, what do you mean by effect? How do I say that this is affected and this is not affected? What do I look at to know that it is affected?
yes, sir. Due to those external loads, there is not much of the internal stresses which are developed in static determinate structures.
So if there is a thermal expansion of some members, or there is thermal load acting, then the forces will not change.
Yes, sir. The forces will not change
only because of the mechanical loads.
Yes, sir. Yes, sir.
Okay, good. Yeah, fine. Any other differentiating factor between a determinate system and indeterminate system? Okay, I'll call again. Salman? Salman, your mic is not working, it seems. Sairaj Bhupati?
Sir, in terms of stability, can we say, sir, like, means not stability, sir, is the system stable or unstable in that way, can we say, sir?
No, I'm not talking about stability yet.
Okay, sir.
Stability is a different matter.
Okay,
I'm talking
sir.
about determinacy. So determinacy, there are two things we have found so far. One is that the system is, if it's a determinate system, equilibrium equations are sufficient to solve the system.
Yes,
But
sir.
somehow as an engineer, that might be a mathematical definition that works okay. And you can find formula and you can fit the number of equations in the number of unknowns and fit the formula. But as an engineer, it does not speak for much to me. One other definition that Prithvi has, not exactly a definition, but one way of knowing it is that Prithvi has suggested is that if there is a kind of a thermal expansion or this kind of deformations or imperfections in the system, for an statically determinate system, you will not have any member forces arising out of that. But if it's an indeterminate system, then there can be member forces arising out of it, which is correct. So that is another way. Any other way of knowing it, or if not knowing, at least one distinguishing feature between determinate and indeterminate system?
Sir, determinate system means so, with only equilibrium equations we can solve the whole structure. Means with one type, means static or dynamic, by considering forces or displacement we can find the means unknowns. But in the indeterminate structure, in indeterminate system, we need to consider one more type. Like when we consider force, we even need to compatibility equations for solving
That is exactly what Mohan had started with. Mohan, he had given exact same definition. That is okay. That is just a repetition of what Mohan had said. And when you say you can solve the entire system, can you tell us what do you mean by solving the entire system? What are the parameters you are solving for? What are the unknowns that you can solve for using the equilibrium equations?
Sir, reactions,
Yeah.
Bending moment.
Bending moment, internal forces.
Internal forces, sir, and shear force.
Bending moment is basically one type of internal force. Yeah. So
Yes, sir. And shear force. That's all. That's yes,
all.
sir.
Deformations, can you get?
Yes, sir. Means kinematic in kinematic determinacy, we can means if we consider kinematic determinacy, we can find.
No, I'm not talking about. I'm not talking about kinematic determinacy or indeterminacy. I'm talking about statically determinate systems. For a statically determinate system, once you get the internal forces from that point on, can you also get the deflections without
yes,
having
sir,
to? Yeah.
We can get, I guess.
Yeah, basically you don't necessarily need compatibility, but you need material properties.
Yes, sir.
Material and cross-section properties. Okay. Any other? Thanks, Sairaj, but I didn't get the answer that I was looking for. My question was: is there any other distinguishing feature between a determinate and an indeterminate system?
Means
Monish? Yeah, please. Monish can try to answer. Monish, you have something to add?
So maybe based on boundary conditions.
Yeah. Say the full sentence. I don't know what you're meaning by.
In a statically determinate structure, if we remove any boundary conditions, like it will become indeterminate. For an indeterminate structure, if we remove it may come as determinate structure.
Okay. So determinate system does not become indeterminate. Determinate system becomes unstable.
Unstable.
Okay. Yeah. An indeterminate system may become unstable, but it may also just reduce its indeterminacy or may become determinate. And it's not just the boundary condition, all kinds of constraints. Okay, that's very good point. I know at least one more point, so I'll keep pursuing that line until somebody answers that. Krishna Katyal.
So nothing specific to add from Prithvi and Mohan.
Okay. Krishna, I'm intrigued by your surname. Where are you from?
Basically, I'm a Punjabi, sir. But
Punjabi,
right
right?
now,
Yeah, it's more of a Punjabi surname. That's what I was wondering. So where are you right now?
so right now in Bangalore. Sir.
Okay, fine. Yeah. Moving forward, Indra, you have something to add?
No, sir, the same thing only I thought about.
Okay, Dipsy.
So same thing. I have nothing extra to add on this.
Okay, Amulya.
So same thing related to equilibrium equations.
Okay, Nikhileshwar.
No, sir, same thing.
Okay, Leo, you are my last hope. You have to give the answer now. One more distinguishing feature.
So actually, what I think was that Monish said, like in a statically indeterminate structure, there will be over so many redundant, means so many constraints. So if you reduce that redundancy, it will change to simple determinate.
Monish exactly said the same thing, I suppose, right? Yeah. And anything else?
In static indeterminate structures, it will be more complex. Even though more complex, it will be more stable. I think like that.
Don't pull in stability into this argument, this discussion. Stability is a different animal. But yeah, basically the same thing again. Like you have more constraints coming in, so it it offers you a stiffer system. But again, stiffer is also a bit of a. Okay, I had missed some people in the beginning. I started from Mohan, so maybe I can start with Asadullah again.
So,
yeah.
Actually, in the indeterminate structure, the reactions also depends on the material and the cross-section properties. Whereas in
I love you, Asadullah. Very good. Thank you. Yeah, I was waiting for this answer. I don't know whether you have the lecture notes open with you. I don't mean to demean what you just said. Wonderful. Very good. So, yeah, thank you. I was able to conclude that discussion. I was hoping to. So basically, I'll go one point at a time. Asadullah, do you want to complete that thing? I followed what you are saying, so I just want to continue with the lecture. I hope you don't mind me cutting you off. Okay. Very good. So, all right. So, basically, all of you understand, right, what a determinate system would typically look like and what a typical indeterminate system would look like. So, if you have, let me project this screen. Okay. So, this system, would be a determinate system. This system would be a determinate system, right? Cantilever simply supported. And we are talking about plane beams. This system would be an indeterminate system. Okay. And yes, when that definition that you have been told number of times that is applicable, the definition is that equilibrium equations are sufficient to solve this system. When I say solve, I mean calculating the reaction forces and calculating the internal forces. Okay, whatever are the applicable internal forces on these two systems. Just from the equilibrium equations, you can probably not solve for deflections, because for deflections you still need the constitutive relationship and all those things. Okay, cross-section properties, constitutive relationships, the kinematic relationships, meaning the relationship between curvature and displacement. Okay, those kind of relationships are still required. So purely from equilibrium equations, that is sigma f and sigma m, they are equal to 0. You may not be able to get the deflection, but that is not what the definition of solving is. The definition of solving typically means calculating all the forces, internal forces and reactions. So that much you can do purely from equilibrium equations on these systems. But on this system, you cannot do that, right? That is okay. That is the accepted definition. I don't have any argument with that. But as an engineer, that definition does not really help me very much. Okay. Then I have to look for some other clues as an engineer to quickly identify and understand the behavior. So basically, a determinate system is a simple system versus an indeterminate system, which is more complex. And again, simple and complex are more vague terms, right? What may be simple for me will be complex for you, or other way around. So I don't mean to again put you down. What may be simpler for you may be complex for me. All right. So how do we say what is simple? So basically, and all these definitions, all the things that I'm talking about are not exactly black and white, right? There is always some vagueness in these definitions, but they help a lot as an engineer. So a determinate system is a kind of a system that is just held in place with the minimum number of supports and constraints. Okay. So if I remove any of these supports on any of these systems, so for example, this is a fixed boundary condition here, right? So if this fixed boundary condition for a plane beam is offering 3 constraints: axial constraint, lateral constraint, okay, and rotational constraint at this point, at the fixity. If I remove any one of the 3, the beam will fly off in that particular direction. So if I remove the rotational constraint, it will start spinning about this hinge. If I remove the axial constraint, the beam can simply slide off in this direction, and so on. Same thing would happen here. If I remove, there are 3 constraints here, 2 here, 2 horizontal movement, vertical movement, and vertical movement. These 3 are constrained here. So if I remove any of the 3, the beam will start moving around, okay, without offering any resistance. And what is what is the basic meaning of stability? When a system displaces without offering any resistance, then that's an unstable system. For a system to move, it should offer a resistance. Okay, and for a linearly elastic systems, that resistance should be proportional to the amount of movement, amount of displacement. Whenever a system moves without offering a resistance, that is called unstable system. Fine. So in your 8th grade, you must have been taught, or 9th grade maybe, you must have been taught about the neutral. There are 3 types of equilibriums: neutral equilibrium, stable equilibrium, unstable equilibrium. So unstable as well as neutral equilibrium, both of them will be classified as unstable. Only when you have a stable equilibrium, that will be stable equilibrium. Okay, so that is one definition. In this case, what happens is that you needed only this much of support. So if I mix the 2, if I take the constraints coming from this system, and if I take the constraints coming from this system, I add the 2, I superimpose them. Okay, then I get this system. So basically what is happening is that I am providing one extra constraint. Let's say this one is one extra constraint in addition to what was minimum required. So this one was the minimum required, but I added one extra constraint. So if I just remove that constraint, the thing is not going to fly off. It will not become unstable just by removing one constraint. But it is not universally true. In an indeterminate system, you may still find some kind of a constraint which you can release and the system will fly off. For example, This fixed boundary condition consists of three things. Okay, so basically what, if I can just represent, it has these three constraints. Okay, fine. So if I remove this one, no issues, it is still stable. If I remove this one, any issues?
The beam will go up.
Let's see. So what will it look like? It cannot move in the axial direction here. So basically it is this kind of a constraint, and it cannot rotate either. So it is this kind of a constraint. Let me erase it, try it again. So the constraint will be this kind, right? So it is offering axial constraint. It's a slider basically. Yeah, this is a stable configuration. Fine. So if I remove this one, still no issues. That is fine. If I remove this one, the axial force, this axial constraint, then what happens? Imagine vertical movement is restricted, rotation is restricted, this vertical movement is restricted, but the whole beam can simply slide in this direction. Correct? So that is unstable. Okay. So basically what it means is that at least some of the constraints you should be able to remove without making it unstable. Then it is an indeterminate system. It does not mean that you can remove any constraint. Okay, but at least some of the constraints you should be able to remove and still keep it as a stable system. Okay, make a note. It is not like you can remove any constraint of your choice, because some constraints are so critical that if you remove them, it will become unstable still. But you should be able to remove at least some constraints. You can select them intelligently. Here you cannot remove anything. Here in this beam, you have these three forces, three constraints available, right? And you cannot remove anything. Anything you remove will make the system unstable. Okay, you got it? Now, the definition that Prithvi had just told us, this was naturally fits. So he was talking about thermal expansion, etc. But basically, it's a more generic definition. So there may be reasons why, well, let's say I want to make this beam. I'm making a bridge, and in that bridge, I order a girder that comes from a factory. Okay, and at the site, I prepared the foundation. So my foundation is ready. Piers are ready at these heights, and then I ordered the girder. The girder has just arrived, and when the girder came, I found out that girder I had ordered is to be exactly 8 meters long, but they provided me, instead of 8 meters, they gave me a 7.95 meter long girder, or 7.99 meter long girder. Okay, it's 1 centimeter short. Then what happens? Will I be able to use that girder here? If I was planning to use it as a simply supported system, just putting it on two bearings, okay, 1 centimeter is not a big deal. It's not going to introduce any forces on the system. Only thing is that this roller has to adjust by 1 centimeter. And that roller is, the purpose of the roller is that it can adjust a small space, so a small gap. So that's why I'm keeping it very small, like 1 centimeter or something like that, in comparison to total length of 8 meters. So as long as this roller can adjust that much of deformation, you don't have any forces acting on this beam. However, if my beam was supposed to be this is how I had planned the beam to be. Okay, now you can see the difference between this and this, right? This is system 1, this is system 2. You can see the difference between 1 and 2. Why? So in this case, I had ordered an 8-meter long beam, okay, and I get to, let's say, let me give you a practical example rather than this one. So this system could be, I have two very stiff columns, and I have a beam that is supposed to connect these two columns here at this level. Okay. Now, the columns have these angles that are projecting out where it has holes, and this column also has an angle which is projecting out, which has holes. And then I bring in the beam, and the beam has also holes. Now the holes are exactly located where, so the holes of the beam are supposed to match with the holes of the angles that are welded to the column. Okay, so this could be, I mean, if these angles are stiff enough, and if the columns are still stiff enough, we can idealize that as this kind of a system. What happens if the holes are not aligned perfectly? Meaning that the space between this hole and this hole or the space between the two columns or the respective locations in the two columns is, let's say, 8 meters. But when I get the beam, the space between the holes in the beam are, instead of, so this spacing, the spacing between this hole in the column or in the angle is 8 meters. But the beam holes are 7.99 meter away. Okay, then what will happen? Can I still put that beam in place? Can I? I can still. I mean, maybe 1 centimeter is maybe a bit too high, but let's say 995, maybe 5 millimeters. Okay, I may somehow still be able to ram it through. I can push the columns in a little bit and apply some jacks or some kind of a restraining force to push the columns in by 2-3 millimeters and somehow force the beam in. But in the process, what do I have to do? Friends, you have to speak up. In the process, I will introduce
Stresses. Compressive stresses.
Yeah, tensile stresses. If the beam was shorter than what was required, then the beam will be in tension. So tensile stresses will be introduced. So basically, that is called a lack of fit. Okay, so determinate systems can accommodate all kinds of lack of fit. Small lack of fits, all kinds of. Indeterminate systems can accommodate still some of them. Okay, so you had this beam. This is an indeterminate system, right? The example that is shown here. If the beam was slightly longer than what you needed, still it can accommodate that. It doesn't have a problem with that. But if the beam was curved, so I ordered the beam, I have the foundation and everything ready. So this support is ready. The exact place where the beam is supposed to enter, that slot is perfectly ready. It will just accommodate the beam there. And then this support is also ready. I have already kept the foundation ready. Now I bring the beam, and the beam is turning out to be slightly curved. So here I fix the beam into this slot, but then the beam is not really coming and touching the other support. It is curved because it is imperfect. It is lack of fit. Then what do I have to do to make it get a support from this roller? I have to push it down. Right? So when I push it down, I introduce stresses. So you cannot accommodate any lack of fit or all kinds of lack of fit in an indeterminate system without introducing stresses. But all kinds of small lacks of fit can be accommodated in determinate systems without introducing any stresses. That is one very important distinction. Here are some examples of you can think of, like this I have given you the example of. This also I have discussed. This I have discussed. Truss also, for example, this is an indeterminate truss. So if, for example, this bar, you can see this is a continuous member, which is almost like a beam. Okay, so it is not a true truss in that way. If this bar is slightly longer than what is required geometrically, okay, it's slightly longer, then how will you accommodate? You can make the entire truss first. This beam you can place, these two members you can place. Then you try to fit this member in place, and it won't fit because it is slightly longer. So all you can do is either bend this beam or stretch these two members. Either way, you are introducing some stresses. Here is a hinge here in the horizontal member. There is a hinge here. Now, in this kind of a system, before you bring in this member, this was an unstable member. And as soon as you put this member in place, then this becomes stable. But now, if this member was slightly longer than what was geometrically required, you will very easily accommodate that by making this beam go down slightly without introducing any stresses, because you have a hinge here. So it will very easily deform to accommodate that small lack of fit. So that's why all kinds of lack of fit can be accommodated. In this case, some can be accommodated, but not all. Okay. This is the basic definition that you have been taught. So I'm not going to elaborate more. Okay. Another very interesting feature that Sadullah finally answered was that, let's say I have this system. This is the cantilever, right? The fourth one. If I want to know what is the bending moment diagram, I can tell the bending moment diagram without even looking at what kind of shapes or cross-section sizes I have. The bending moment diagram for this beam will be this, right? A straight line. Agreed? All of us know that. And it does not depend. What will be the bending moment diagram of this beam? Exactly the same. This will be PL or minus PL if you want to call hogging as a negative moment. This will also be PL. Fine. It won't depend on what kind of cross sections you are using here. Here the cross section is same uniform. It is varying here, but the bending moment diagram does not change. In this particular system, that is not true. So this is an indeterminate system. The bending moment diagram for this case, how will be the bending moment diagram? Something like that, right? And it will be dependent on the values. The shape may still be the same, but the values here, these values will vary based or will depend on the cross-section sizes. Same thing is true here. So here, if you apply force P, how much reaction are you going to get on each side will be dependent only on the geometry. It does not depend on which member is bigger or smaller. If you are applying P force here, you will get P by 2 reactions here. But here, same thing here. If you apply P force here, you will get P by 2 reaction here. That means this is a determinate system. If it were an indeterminate system, then that would not have been true, or probably could not have been true. So it does not, the internal forces and reaction forces do not depend on material and section properties, but in this indeterminate systems, they depend on relative properties. So internal forces, they will depend on relative properties. So if this section is stiffer than this section, then whatever force you are applying, a major portion of that force will be transferred to this side than to this side. Okay. Any questions from this part? I think I'm almost out of time. So this, I would recommend you go through this definition of this method. I'm sure you already familiar with various other methods to calculate the indeterminacy. So here is one method shown here. You can go through this, or you can keep following the method that you're familiar with. So the next two slides I would recommend that you go through. In the next class, I will talk about stability a little bit. Okay. Any questions? I hope a few additional perspectives were added to the discussion on determinacy and indeterminacy. Some things that you might be familiar with, but not exactly knew what it was. I hope I have explained that a little bit. Okay. Any questions or any points of discussion? All right, then. I will conclude the class today. We'll continue in the next class.
Thank you, sir.
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 Thank you, sir.